Hello everyone. Today we are going to talk about our final project for robot manipulation course, building dual robot air hockey system via inverse kinematic control state machines in Drake simulation. So first, classical robotics tasks like pick and place or assembling mainly focus on static settings and single agents. However, some sports like air hockey includes a fast, dynamic, and multi-agent game. So our question is, can we build a system with two robots play air hockey automatically? Here, we first set up our simulation environment. So our design goal is to first simulate the high-speed puck movement and then simulate the realistic puck paddle and puck table collisions. In the simulation, we have one air hockey table with two Kuka players, and each of them held a mallet, and there is a puck on the table. There are some key parameters we need to fine-tune that. So the first is the mass of mallet and puck, and then it is the freak coefficient for the static and also for the dynamic case, and also for the energy dissipation coefficient. In order to finish a successful strike, we build a strike trajectory with inverse dynamics, kinematics, and keyframes. So we define our whole trajectory in four keyframes. First, we have an initial frame, and then we have a pre-approach frame that is slightly towards the puck and the goal. And thirdly, we have the approach frame, and after approach, we have the post-approach frame. A special case is that when a puck is very close to the wall, we just use the wall to reflect them to the goal. And we test our strategy in static and dynamics case. We can see that our strategy can successfully strike the puck into the goal. We also do some analysis for the successful rate. We just randomly initialize the position, and we found that when it is in the static case, we have 56% of success rate. And when the velocity increase, the success rate decrease. Now it turns to high-level planning part.
So after we have a low-level controller which can strike the puck for a single robot, we want to build a high-level planner so that the robot can play the game continuously and interactively. So in our high-level planner, we have three different states: the rest state, Caroline strike state, and the strike state. So in the rest state, if the puck is entering the home area, then we start to calculate the strike trajectory. And if we find a valid strike trajectory, then we start to execute it. Initially, we plan to have a defense state, but we found that offense is often sufficient as a defense strategy. To test the feasibility of our system in the dual robot air hockey, we roll out 10 different games and record the score, the game hand distribution, and the average time. We can see here that our dual robot system can autonomously play the entire air hockey game, and the win rate for each robot is the expected 50% because they use a similar low-level controller and high-level planner, and each game lasts around 2.5 to 5 minutes, and the average time between each goal is around 30 seconds. Now we will play a video that demonstrates that our robot can demonstrate sufficient non-trivial rally of multiple routes, try and block here. So to summarize, in our project, we have built a simulation environment to simulate high-speed dynamic of a hockey game. And in the single robot case, we use inverse kinematic to trace strike trajectory with decent hitting accuracy of 50% for the static case and 30% for the moving case. For the dual robot playing system, we demonstrate that the system can play an entire air hockey game via state machine, and also demonstrate that the system demonstrates non-trivial rally of multiple rounds of strike and block. So during the project, we had several takeaways and also future improvement. So we found that dynamic object manipulation require both future both estimation and robot trajectory time estimation. And for the future improvement, we can use a dynamic models for more accurate future both estimation. Also, in our high-level planner, we use a rule-based approach, which is sufficient to sustain the whole game, but lack diverse and adaptive strategies. In future work, we can use reinforcement learning to learn adapted high-level strategies. Thank you for listening to our project, and I hope we enjoy it.
Thank you.